Thank you everybody for joining us today. My name is Sean Maurer with the Smart Energy Design Assistance Center. Today we're going to be talking about field applications of mechanical insulation. Joining me today is Bob Flynn from the Heat and Frost Insulators up in Chicago. Thank you for joining me today and helping with this presentation. I'm going to start with just a quick overview and some housekeeping notes, and I'll hand it over to Bob. He's going to run most of the presentation here for us, and I'll chime in on our energy code implications. But today's learning objectives, summarize a little bit about the energy code requirements for mechanical insulation. We're going to cover real-world insulation examples and look at how energy code compliance is impacted by those installation practices. We're going to identify some design details that can help avoid those common insulation installation issues and ensure that you're compliant with the energy code when you're installing your mechanical insulation, and describe the energy and maintenance impacts of improper insulation installation. So who we are here at the Smart Energy Design Assistance Center. We are an applied research program at the University of Illinois with the mission to reduce the energy footprint of Illinois and beyond. We assist buildings and communities in achieving energy efficiency, saving money, and becoming more sustainable. We help facilities become more energy efficient through education, research, and advocacy for a greener future. And this training program is one of the aspects of our services to help achieve those goals. Our training today is provided with support from the Illinois Environmental Protection Agency's Office of Energy, and we thank them for their support of our program. We do offer continuing education credits as part of the training today. We are an ICC certified education or preferred education provider. We also work with the American Institute of Architects to provide continuing education credits for the architects that are joining us today. As part of your registration, you should have had a form input for your AII member number, so we'll take care of turning in those credits for you. For everyone else, if you're a PE or some other credential that you need, we do provide a certificate of attendance for tuning in today so that you can self-report those continuing education credits to those other agencies. As part of our energy code training program, we do provide technical support and assistance to people on the energy codes. You can reach us at energycode@cdac.org. That's actually been updated. It should be energycode@illinois.edu. And we also have that 1-800 number for quick questions. We do prefer you reach out to us by email. It gives us a chance to dig in depth into your question and get you the best response possible. But if you just need some quick support, that 1-800 number is available to you. We also have a number of online resources available at our website, smartenergy.illinois.edu/energy-code. All our previous workshops and webinars are hosted there, as well as some self-paced online on-demand training modules so that you can learn the codes at your own pace. Today's webinar is part of a series of lunchtime webinars that we're offering on the energy codes. This year we are covering kind of code basics and being familiar with how the code is structured and put together. Our next lunchtime webinar on the 14th, we'll be touching on the stretch code for the residential applications. And then we'll move through some other topics as far as how we actually use the energy code at our next Q&A session. So we'll hope you join us for our future webinars. We are also conducting some in-person workshops. Our first one was completed in Springfield last month. For those of you that were there and able to join us, thank you for attending. We'll also have one coming up north. We're still working out the location, but sometime in March 19th, we'll be hosting a similar in-person presentation on just energy code basics, how to get through the energy code, using different passages of that code to simplify energy code compliance, make it easier to comply with the code through design choices. Access updates on the Illinois Energy Conservation Code. Sometime this month, we're expecting JCAR to approve the Illinois amendments. We're continuing to update our website with the latest information. There's a JCAR meeting today. So hopefully we'll have some updates later this afternoon on updates to the 2021 IECC. Access to all the codes is also available on our website, and we've got the links included here as well. Once the Illinois amendments are official, we'll have a link to those on our website as well. Right now, we've got a link to the proposed amendments. We've got a link on there already to the 2021 IECC. We also have links to the Chicago Energy Transformation Code so that you have a one-stop shop to gather all that information at our website, smartenergy.illinois.edu/energy-code. Most of the content for this presentation is also going to apply the Chicago Energy Transformation Code the same as it does for the 2018 IECC. If you're still working on projects under that code compliance, for anyone, hopefully later today, we'll find out the approval for the 2021 IECC. If you're working towards those, again, the requirements are very similar. So at this point, I'll turn it over to Bob Flynn. If you want to talk a little bit about the heat and frost insulators, and we'll get into our presentation today.
Thanks, Sean. Yes, we're with Local 17 Insulators out of Chicago. We cover 23 counties in Illinois and 3 Northwest Indiana, basically northeastern corner of Illinois. We comprise of one of 100 locals out there of our total international from the United States as well as Canada. I've been an insulator since just out of high school in 1988. I got into the program in 1995 and ended up working in the field in many different facets of the trade, whether it was commercial, industrial, oil refineries, nuclear power plants. And one of the things that we wanted to team up with CDAC was to educate people about what we do in mechanical insulation. And that's what brings us together today. So we hope there's a lot of questions, a lot of answers that you, a lot of answers to those questions just with our presentation here with Sean and I. So if we get, when we begin here with some of the goals of the presentation, and that's to further educate the group on some of the shortcomings of what the heat and frost insulators see in the field, such as value engineering or cutting corners, engineering issues, or poor execution of projects through our that we see. And one of the most important things that if you don't do the project correctly, you'll have corrosion under insulation, or CUI, result in many practices in this that you'll see in this presentation could have that. Corrosion under insulation, CUI, occurs when humid air penetrates insulation to cold pipes or duct. Wet insulation degrades performance. Wet insulation can harbor mold, moisture on metal pipes which cause corrosion. This is an example of a cleanup on a job, and when they removed the insulation, that's what they saw. This is probably the most important aspect, getting insulation right on mechanical pipe systems. CUI leads to premature failures of piping and potential extensive water damage to other parts of the building assembly when pipes fail. Proper insulation and installation of maintenance can help a building's owner avoid hundreds of thousands of dollars in repairs each year. Code provisions addressed with CUI, not directly addressed by the code, but maybe I'll lead over to Sean when it comes to some of that stuff, if you'd like to talk about the codes, Sean.
So corrosion under insulation isn't directly addressed by the energy codes. However, as we go through the energy code and look at some of the language that's contained in there, we can see how it impacts the actual installation practice of insulation for mechanical systems. So C403.12.3.1 requires exposed piping to weather and exposed insulation for duct systems exposed to weather. It has to be protected from the elements, mechanical damage, wind damage, rain, water, moisture, UV. So the insulation can't just be exposed to the elements where it can degrade. It has to have a protective covering to it. This doesn't list the same requirement for indoor insulation. However, C303 requires insulation to be installed per the manufacturer's instructions. And those instructions often require insulation, particularly on chilled water piping, to have an airtight jacketing on it to prevent moisture and humid air from getting through, contacting that piping and condensing and causing the corrosion issues. So we typically see that all-surface jacket or PVC jackets as common air and vapor barriers on interior insulation. And so some example images here on the top properly insulated, airtight. You can see all the joints are taped and sealed. There's end caps in place on that insulation to prevent air and moisture from reaching that piping and causing corrosion issues. Another example just below that of an instance where maybe sometime in the past someone needed to access this joint and repair a leak or something like that. The insulation wasn't properly reinstalled. Or somewhere nearby there was a penetration through the jacketing material that let some moisture in, and that caused this corrosion damage.
So when we talk about preventing CUI, maintenance workers will often step on the mechanical piping to access valves, fittings, fan belts, and other mechanical components using rigid jacketing in areas where such practices are likely to provide alternate access routes to elevated fittings and mechanical components can help preserve the insulation system's integrity and performance. Using removable insulation on valves and other fittings ensure the insulation can be removed for maintenance and access without damaging the insulation. It can be replaced and maintained in the insulation integrity as a whole as a piping system. So that's one of the reasons that we do when it comes to preventing damage to insulation, as we were seeing some of these things that we will be seeing going forward. But some of the correct practices follow installation instructions for insulation jackets, seal insulation on the ends, don't leave open to the air, provide protection provisions where damage is likely. Horizontal insulation is often used to step up on valves and fittings, like I spoke earlier. Using rigid jacketing and nearby ladder for supporting would help prevent damage and a longevity for the piping system. And insulation around the fittings, often removed for maintenance, should have a possibility of using a removable or even a bag system in its place.
And just a quick note here, the example image, you can see there's a little bit of an error. We're going to point that out here for you. There's a little bit of air gap where this end cap hasn't been sealed properly, or the sealant was applied, but there's a crack in that insulation. If this was chilled water piping, this would be a concern for corroding that piping, getting moisture in that insulation. As this is hot water, it's not as much of a concern, but still something to be aware of in practice, particularly on these ends, to make sure that they're sealed up properly.
So let's talk a little bit about these removable bag systems, otherwise known commercially as sweat bags. These bags were originally intended to do valves and work on these different stations when it comes to maintenance work. What we're seeing sometimes in the field is that they're used to insulate the system fully. That's not what their original intent was. It was basically put in place to get access to these valves and these strainer systems. One of the things that we've seen is that if they're not done properly or they are messed up with in any way when it comes to the functionality, that would that would void the warranty on these sweat bag systems. So they do play their role, they do play a part, but as a whole insulation system as a whole, to save money, you're probably better off using an insulation system, traditionally insulation system. Yes, one of the questions here from one of our people who are in the audience, it's important to note that these are originally intended not to be altered, as stated. Yes. So flexible insulation systems designed to prevent condensation when used with pipe insulation. These are what these bags are for, replacing permanent insulation for valves, strainers, and other oddly shaped fittings. When used and maintained properly, can perform well, but only if installed properly, as stated.
One thing to note here for these, just in the example images, you can see there's the Velcro closure for the bag. They've actually cut next to that Velcro in order to fit the strainer cap out through the bag, which now the bag is open. It's not providing any vapor protection for that system. So these bags, once you modify them, there's no longer the no sweat warranty. They're not going to be guaranteed to work as they should. So they need to be properly sized and fit around these fittings, which is where we touch on the energy code implications. So again, kind of limited sections. You're going to hear me mention the same things a lot today. But if insulation is compressed, the R value is reduced from the requirements in Table C403.12.3. That table lists for specified conductivity range and thickness of insulation to achieve an R value for that insulation. If you use a different conductivity, you can get away with thinner insulation if you have a less conductive insulation material. But again, that table has those specifications for thickness and typical conductivity ranges of insulation used. If you're installing these bag systems where they're super compressed, you're not achieving that thickness, so you're not in compliance with the code. Flexible insulation is also prone to mechanical damage that degrades performance over time. So if you're using these systems on the exterior of the building, there needs to be some additional protection. These bags are flexible. They don't provide protection themselves except for vapor transmission. So you also need to have protection from mechanical damage, wind. When these are installed on the exterior of a building, they do need to have tape or sealant to seal the ends to the pipe insulation or on either side of the fitting, and to seal that Velcro seam on these so that moisture can't penetrate in. Just some examples from the inside of buildings where these bags have been installed. You can see there's some compressions on these hot water pipes where you can see all the heat leaking through the bag systems. So something to be aware of, again, is the energy code in C303 requires that insulation be installed according to the manufacturer's instructions. So when you're looking at these no sweat bags, they do have an installation practice, which is detailed here.
Yes, Sean, that's a great point. And as well as a lot of the building inspectors and people that we speak to at different functions, they say if it looks good, usually if the pipe covering looks good, it's probably going to be okay. The last slide actually shows with a infrared gun that if it's not done properly, there's a lot of energy that escapes. And those pictures in the last slide actually show that. I think, Sean, there might be a question from one of the people in the audience regarding valves. Does the code require insulation at valves and strainers? If it's Sean, maybe you want to take that specifically. That question.
For any fitting on pipe sizes greater than 1 inch in diameter. So if it's for 1 inch or smaller piping, the code does not require that strainers, fittings, and things have insulation on them. But for larger components of the piping system above that 1 inch threshold, yes, the code does require insulation at those fittings and joints, valves.
And actually in the field, the insulation is very easy to cut when you're dealing with fiberglass. You can actually dig out for for something that small that actually doesn't say it. It doesn't cost any time or effectiveness to the job when you can just dig out for the valve as well, or the strainer as well, as long as they can get access to it. Okay, the next one is the proper no sweat bag installation. Insulation should not be compressed, as Sean stated earlier. Bags and tightly sealed to the neighboring insulation to prevent moist air infiltration. Outside bags need to be sealed with a Velcro seam to the neighboring insulation with the tape and sealant for water intrusion protection. Bags sheathing is unmodified, providing continuous vapor protection around insulation. Bags don't provide mechanical insulation protection. It's the insulation inside that actually does the protection. The bag itself is almost as if it was a vapor barrier. Building maintenance standards must note care around bad insulation. And once again, as stated, if you modify the bags, it does void the warranty.
Before we go on to the next issue, we did have one more question about does the code prevent the use of insulation material that absorbs and holds water on chilled water piping versus hot water piping? Uh, the code is material agnostic for the most part. For applications, it relies on proper installation practices. So if you're following the manufacturer's installation instructions for these piping insulation systems, fiberglass is a very effective insulator and can be used on chilled water piping, but you have to pay attention to that exterior um, jacketing on it, that is airtight and vapor tight, so that you don't have corrosion issues underneath that insulation.
Okay, so thank you for that question. Tight engineered and installed piping. So we see a lot of this when it comes to job sites. There's a lot of material, a lot of action going on the job, and you have a lot of different trades working together, trying to get the project done. The picture on the left actually shows um, a, a uninsulated pipe with a conduit running through the same hanger. That, of course, is would be unacceptable. They'd all have to have their separate spots, and either piping would have to be moved or the something would have to be adjusted. So one of the things that we see on these jobs are a little bit of engineering issues, and that's what we're going to talk about now. Common installation issues is mechanical systems often have limited space for piping and insulation. Uh, can lead to interrupted or compromised insulation. If insulation is compromised, it can lead to an unintended energy loss or corrosion of components. So this is very common when we see in ceiling plenums where space is premier and proper coordination between trades is needed to avoid this situation.
So on the
Once again,
energy
this is
code side, looking at those impacts, the example images here, this pipe was installed really close to the floor, where you can only really fit insulation on top of the piping, and it's uninsulated on underneath on the floor. So they just kind of covered it up with the boxes that you see on the right-hand side of the image here. This would not be a code compliant installation because that pipe isn't insulated all the way around the pipe. So you're going to have energy losses into the floor structure there. So again, going back to C403.12.3, you have to have a certain thickness and conductivity rating of insulation material around that pipe that gives you, when you combine those together, gives you an effective R value for installation. And so similar application for domestic hot water piping, if you have that in a building in C404.4. You have to meet these insulation values. So when you take that C403.12.3 table and you multiply the conductivity rating of the insulation by the thickness, you get an effective R value that you need for that insulation. If you find a material has a lower conductivity rating, you can get away with a thinner amount of insulation as long as that R value is achieved. And so there has to be some coordination in both architectural design when you're looking at the drawings and things like that, coordinating with the mechanical contractor when they're coming up with their design drawings as well, and then actual installation in the field. In this case, had there not been this supporting pad poured on the floor here, the floor may have been low enough to allow for proper insulation, but then they poured this slab underneath this piping for some support purpose, and now the insulation can't fit. And so this becomes a non-compliant for energy code purposes. And now it's a pretty major retrofit to undo that and correct it.
Tightly engineered and installed piping. Designers need to detail proper spacing on plan drawings, as Sean was alluding to in the last subject. Often mechanical and plumbing contractors are not the same as insulators. Usually they're insulators are subs of mechanicals and the plumbing contractors. There needs to be maintained spaces of tolerance for insulation to be added using brackets, spacers, mounts, to maintain spacing. So the project manager or the construction manager should be in coordination between the tradesmen to ensure correct installation that meets the specification of the designer. One of the things that we see is there's a, a venture clad, it's called. It's a cladding that goes on the outside of ductwork. It's been replacing metal from previous jacketing applications. The problem with this system is that it has to be done. It has to be installed at temperatures above 40 degrees Fahrenheit. So adhesive cladding, this is an adhesive cladding that are common materials used due to their ease of installation. Carefully following the manufacturer's instructions as stated, it should be installed before above 40 degrees and must be rolled out for a proper adhesive pressure, clean prepared surfaces for proper adhesion.
So on the energy code side, one of the key things here is that the energy code for exterior insulation protection states that adhesive tapes are not permitted. So when we start looking at this VentureClad system, how do we determine whether it's an adhesive tape versus a cladding system? If the VentureClad system is integral to the installation, it's part of the installation process, then it's not considered an adhesive tape. It's considered an integral part of that installation system. But the main reason the energy code avoids and does not permit the use of tapes is because when you have to do maintenance on this work, you need to access something underneath. If you pull that adhesive tape off, it's going to damage more of the insulation than just where you're pulling a tape off, because it's going to rip out chunks of insulation that are adhered to that tape. Also, in general, tapes aren't broad width like this VentureClad system. So you can get compression, you get inconsistent application, you can get gaps, cracks between the seams of the tape that can allow moisture penetration and damage to the insulation underneath. So the energy codes does not allow the use of adhesive tapes for the protection of insulation. When you're looking at the VentureClad system, if it's an add-on component to the insulation, you're using it like the insulation is a separate system, and then you're using this VentureClad to wrap over that, that would not be allowed per the code. Again, we're looking at, it can delaminate. Now you don't have your protection. It can not be properly applied. If you don't properly clean the surfaces that you're applying this VentureClad to, fingerprints, oils, things like that can cause this to delaminate and not stick properly, dust and things like that. So there are manufacturer's instructions for how this should be installed to ensure proper adhesion. That includes rolling it for pressure. It includes cleaning the surface with some kind of either an alcohol wipe or something like that that's going to remove oils, dust, things like that. That a lot of times when you're doing quick installations on jobs doesn't get done properly. And so that's why the code has this prohibition against adhesive tapes in general. But there is kind of that caveat that if the VentureClad is part of an integral piece of the insulation system and not an add-on cladding, it can be code permissible. If it's an add-on separate to the insulation system, then it would not be permissible. It's considered then an adhesive tape type installation. So it can be a little bit tricky to know when the code is going to allow this or not.
Sean, one more thing before we go to this next slide here. If you look at the last picture, the insulation looks really good, really nice job, really tight job. However, many times specs you'll see they're actually asking for a watershed, whether it be at the center, a higher level at the center of the ductwork, or on one side or the other. Have some type of pitch on the top of the ductwork where you actually see the watershed, where the water will actually not end up becoming a part. I'm trying to think of the word.
Ponding on top.
Yeah, it's staying on top, so it actually keeps the water from pooling on the top of the ductwork. So there should be a little bit of a pitch on top of that duct, but otherwise, it's a properly done job. So the next one is a continuing on proper outdoor insulation protection, code compliance insulation, integral cladding or non-adhesive cladding, as Sean stated, adhesive-based sheathing acceptable if part of the insulation system and not standalone sheathing product. Remember, adhesive tapes are not permitted.
And one of the things we talked about earlier, Bob mentioned on the first slide for this section, metal cladding. You used to have this clamp on or bolt on metal sheeting on the outside of the insulation. And then VentureClad's kind of been replacing that product. But you can kind of see here an example of that. It's the aluminum sheeting that clamps around the outside and it's held on by these metal straps. For duct insulation, there's a similar installation process. But that is a non-adhesive based alternative, is those aluminum based cladding systems.
Let's move on to improperly installed ductwork systems that you may see. So insulation, exterior insulation on ductwork installed baggy or poorly sealed duct wrap systems, ductwork equaling pipe when it comes to a mechanical insulation system. Poor ductwork insulation degrades overall system performance and can also create health hazards. So ductwork is no different than piping when it comes to how it should be installed or insulated. The type and quality of insulation will help ensure the system runs smoothly and effectively while saving energy for the stakeholder. Baggy insulation isn't properly supported and compresses insulation on other parts of the ductwork. Ductwork isn't tightly sealed, can allow condensation between the ducts and the insulation. This can harbor mold and mildews. In return ducts, it can be drawn into the system. For supply ducts, air pressure can force these pollutants out into the plenum spaces of rooms.
For the energy code implications, the 2021 IECC section C403.12.1 for commercial buildings denotes the insulation requirements. R6 for ducts in unconditioned spaces. So if it's in a warehousing area, or storage room, or something that isn't heated or cooled, you need to have that R6 insulation. Depending on your climate zone, if you're in climate zone 4 and the ducts are outdoors, you need to have R8 insulation. If you're in climate zone 5, it needs to be R12. If the ductwork is in a conditioned space, and this includes ceiling plenums because they're indirectly conditioned, then no insulation is required. The insulation we usually see installed in these instances is for sound control and not for energy code compliance. But if the energy code is requiring the insulation be installed, then it's that R6 through R12 requirement, depending on the situation. If you're running ducts in building cavities that are separated from unconditioned space, those ducts, the plenum space, whatever it happens to be, if you've got conditioned air flowing through there, you need to have a minimum of R8 insulation between that duct cavity or that plenum space and exterior conditions. There is an exemption in the energy code if ductwork within, or if airflow within that equipment and duct system is less than 15 degrees from ambient temperatures, there's not going to be a significant amount of heat exchange. No insulation is required then. The 2021 International Mechanical Code, if we start looking at that, section 603.12 states that provisions shall be made to prevent condensation on any exterior duct. So we're going back again to the previous slide where we're talking about the cladding system and protecting that insulation from condensation, or protecting that insulation from condensation. So you can see in this particular image here, you've got properly sealed supported ductwork. It's not sagging off the bottom of the the duct here. The sides aren't compressed. You're not seeing distortions to the shape of that duct from the insulation being improperly installed. It's tight fitting to the point where it's not deforming. It's maintaining the insulation value that's intended for this application.
And this one that Sean is showing here, the last one was had a different jacketing. It had ASJ jacketing, had a little bit more of a higher density, while the ductwork in this picture is more of a blanket insulation with a lesser density. However, the same thing applies. As you can see on these pictures, you can actually see the hangers are underneath the insulation. It's not cut into the insulation, or the insulation is around the hangers. They actually, the system itself is completely 100% insulated. without with the hanger support underneath it outside the system. It's tight, but it's not too tight, reducing the R factor. And you can also see that the round ductwork coming off of it is sealed tightly, and the ductwork going into the ceiling as well. Very, very nice job there. So bagging poorly sealed ductwork wrap continued. Properly installed is this picture, as we stated. Uncompressed insulation fits snug to the duct, support as needed for pins. Well, we could maybe talk about pins a little bit. Fibrous insulation covered by air and vapor barrier. So basically, the jacketing is sealed 100%. You don't have any insulation fibers hanging out of it. Wrap tightly sealed to prevent moisture penetration. So baggy insulation could create a moisture or as condensation occurs in voids. So once again, it's important to seal the system 100%. The image on the side shows the insulation is properly installed, insulated, snug, and continuous. So there's different layers, as I told you. As last slide showed, it's probably a 2-inch insulation with a 3-pound density. This insulation you would see here is a blanket, usually done on concealed ductwork, is 1.5 thick to 2 inches thick, and can have a density ranging from 3/4 to even 1.5 inches, 1.5 pounds density.
We did have a question come in. You mentioned venture cladding for the exterior sheathing. Is that a proprietary system, and are there problems with that type of system?
Some of the things that we see, that's a system that came out, a proprietary system that came out to try to replace metal jacketing, as I stated earlier. One of the things that you see is if it's not insulated, you'll see with metal jacking, you'll see when storm events hit where you'll have hail damage and stuff like that. You won't see that damage with the metal jacketing, the venture cladding that you see. You'll actually see the penetrations or little bumps in from the hail damage, or even I've seen in some cases where birds have actually walked on it. You can actually see bird steps on it. So it's not as dense. The density and the protection isn't really there for the duct system.
And again, for the energy code compliance, VentureClad is a proprietary system. There are other adhesive sheathing systems out there. VentureClad is just one of them. But for energy code compliance, the main issue there is that cladding an integral part of the insulation, in which case it's permissible to install. If it's not an integral part, it's an add-on product for the protection of whatever insulation was installed. If you've got board insulation in place and you're wrapping it with this VentureClad, now that's an adhesive tape and it's not permitted by code. So there's a little bit of that fine delineation there between the applicability of that type of cladding system, whether it's permitted by the energy code or not. We do have a question here. Do you need to seal the ducts prior to installing insulation?
Myself, I'm not a tinner or a sheet metal worker, but under my from what I've seen in the past, the system itself should be sealed. So outside air doesn't come into the system. Even if you have insulation around that duct system, it should be 100% sealed with some kind of sealer that they like a gray sealer that they put around the seams of each one of the duct pieces of ductwork. I've seen it where it hasn't been done, and then actually I've just recently on a job saw that they sprayed spray insulation around the ductwork without even sealing the ductwork. There's just a variety of problems that go with that. There's a potential 25-400 flame spread issue if it doesn't have a sealer on it. As it actually breaks down, the chemically breaks down to seal the ductwork. It gives off a chemical reaction, and if you don't have the duct seal, it's actually going inside the duct. So I would say yes. If it was me, I would say yes. The duct should be sealed before the insulation process occurs.
And the energy code does cover that as well. in the duct installation section. I'm not remembering the section number off the top of my head. But duct needs to be installed per the manufacturer's instructions, and then the insulation goes on top of that. So whatever ductwork you install, it has to be air sealed as indicated by the instructions for the manufacturer. And so you do have a leakage class generally, depending on what the air pressure in that ductwork is going to be, that must be met. And so whatever sealing needs to be done to meet that leakage class needs to be done before you install the insulation on the ductwork. If you don't seal the ductwork on the supply side, you can have a pressure issue where air leak underneath that insulation causes it to billow off the ductwork. And you can actually tear the insulation, pop it off of any pins or fittings that are holding it in place on the bottom of the ductwork. So yes, proper sealing must be done beforehand.
This next section is pretty interesting as well. Hydronic system valve handles. Kind of take that for granted that, well, valve handle is a valve handle. It should probably be um, what you would see a normal pipe insulation job, but when the insulation is actually thicker than the pipe handling, the valve handle itself, this is the result that you get on the left side. Incorrect practice of valve handles installation without considering thickness of insulation. Insulation often compressed or comprised to allow free travel of the valve handle. Sometimes the handle is bent too. I'll see a lot of the insulators, they'll actually bend the handle out and cut around it and still do the axis. I don't think that's what it was mechanically intended to do. So the actually a valve extender is needed. The more and more that you reduce the insulation thickness, the more possibility of the break in the vapor seal of the insulation wrap causing a potential CUI that we talked about initially. Damage in wet insulation will not perform well.
So you can see in the image here, they've cut the insulation and trimmed out some of it behind the valve handles in order to fit the valve handles and allow them free motion. You can see in the image there, the jacketing doesn't wrap around that little cutout that they've made for those valve handles. So you've got air penetration here. There's going to be problems with this installation in the future.
And I mean, if he was actually going to do it correctly, or she was going to do it correctly, they should have put some kind of sealer, even if they were going to walk away with that project being done. Not saying that it's a correct way to do it, but if they really wanted to do a professional job, they would probably want to put some kind of sealer to get rid of those that little yellow insulation exposure that you see. Otherwise, it's not really serving its purpose as a weather barrier to the inside of the pipe.
As far as energy code implications, again, comes back to section 403.12.3. And if we're looking at service hot water, C404.4, both of those go back to this table for insulation thickness based on its conductivity rating. And so even around those valve handles, you have to maintain that thickness to be code compliant. So if you're cutting away or compressing the insulation, that's not a code compliant installation anymore. So you need to have those valve handle extenders to maintain that thickness.
And here's a picture of those valve extenders that Sean was talking about. So once again, improper piping support, incorrect. So what you'll do is you'll either have a hanger that'll have the saddles on the right side of the picture, and in the case of the left side, they put the wrong hangers all together on there. So installing the right hanger sizes for the pipe system, installing supports without considering insulation thicknesses as seen on the left side. On the right side, there's usually some kind of hanger or some kind of saddle or some kind of insulation support on the inside, not cause the crushing of the insulation. Once, as we stated earlier, once you start compressing the insulation, the R factor is reduced, and therefore the insulation integrity is reduced and therefore not followed by the code.
So going back to our energy code considerations, we're again looking back at C403.12.3 and C4044 of the 2021 IECC, or any version of the IECC back to, I believe, probably the 2012. They haven't changed mechanical insulation much over that time period. But you have to maintain those R values all the way around the pipe, and that includes at supports. There is one exception where vertical supports are supplied for water piping that allows, in order to maintain that pipe location and not let it shake around as such, where you can have a clamp directly on the pipe that can go through the insulation. But otherwise, in all other instances, you have to have a saddle in place to support the weight of the pipe without crushing the insulation. The hangers need to be properly adjusted in height so that, once you put water in that system, you're adding a bunch of weight to that pipe, where it can sag down a little bit. We've seen some instances where you've got a pipe coming up from the floor on a pump or something. You've got a 90 going across the ceiling, and then the hanger is at the wrong height, where it's actually trying to lift the pipe higher than the elevation of where that 90-degree is near the ceiling, and that causes crushing of the insulation. So you do have to maintain the proper R value and thickness to be code compliant. And also, again, we're looking at back to the administrative section, C303.2. You have to install that insulation per the manufacturer's instructions, and those instructions often include a saddle to support the weight of the pipe and the fluid inside that pipe at support hangers. And so, again, just going back to those manufacturer's instructions is a key component for energy code compliance as well.
And as Sean stated, this often requires coordination between the mechanical plumbers, the plumbing and the insulation contractors. As you can see in this photo here, there'll be step back for a second. Sometimes you'll see some of the insulators as they're dropping the hangers. You're supposed to drop the hangers themselves by the thickness of the insulation. And in some cases, they're not given enough to drop, or they're just not doing a properly good job of dropping the insulation, for example, or dropping the hanger, for example. If they're having an inch and a half insulation running through the hangers, they might not drop the hanger enough, or they might drop it too much, and that's when you have that up and down, that ununiformity of how the pipe was originally hung. So once again, the significance of coordination between the mechanical, the plumbing, and the installer, the insulation installer, is very, very important. Hanger heights uniform, as we stated. Level and include provision for insulation thicknesses, as stated in my explanation. Hanger saddles should be spread to force and prevent crushing. This picture here shows a perfect uniformity of the saddle itself. You don't see the insulation crushed. The width and the size of the insulation diameter, and not the pipe. Installing duct and wall penetrations. A lot of times that you'll see, depending on who the person is, who the installer is, if he's trained or untrained, they might want to butt up to the wall. In this case that you see in this picture on the left, you do not have a continuous running of through the assembly. It's kind of butted right up to the wall, and they put a little sealer on there to try to fake their way through it. They should put something in between the wall, or a lot of times you'll see, even if you have to dig out the insulation a little bit, put some sealer to make it through that penetration. In many cases, sometimes something is better than nothing, but butting right up to the wall is not acceptable. So incorrect common practice, duct and pipe passing through the penetration, but the insulation butts up. Piping ducts is not installed through the penetration, as you stated. At least you dig out a little bit or put something in there, you're having some kind of insulation in the walls. If the penetration is into the chase, it is often missed. Insulation in the chase. Lack of insulation wastes energy, possible condensation and moisture development, and moisture damage to the partition also possible.
As far as the energy code, again, we go back to that table in C403.12.3, where you have to have that continuous insulation along the piping. It has to meet that insulation thickness. There's no exception for penetrations through assembly. So to properly run that insulation through a wall assembly, you need to cut a large enough opening to allow that insulation to go through. And if there needs to be some kind of supporting saddle or structural sleeve through that penetration, it needs to be large enough to accommodate the thickness of the pipe plus the insulation. So you can kind of see an example. This is from our own building out here, where our AC line comes through the building. They do have a little bit of a structural ring there to pass the refrigeration pipe through, but it's not big enough for the insulation. So the insulation stops on the outside of the building. Then you've got uninsulated refrigerant line on the inside of the building. So that would not be code compliant. The other possibility here we see in some buildings where you have firewall partitions made of drywall or something like that. If you butt insulation up to that drywall but don't pass it through, and you develop condensation there, for say it's a chilled water pipe, now you've got damage not only to the pipe from condensation, but it can also get onto that drywall, and now you've got mold, mildew issues on that drywall penetration. So there are some considerations here why this insulation, beyond the energy performance, there's other maintenance considerations as well.
There was a question here, a statement said by one of our participants. I found specifying CalSil. It's a kind of a hard. It's a different type of insulation. Insert on pipe hangers allows these devices to be installed by mechanical contractors rather than an insulator. Then easier for an insulator to insulate between hangers than jackets all over. Cleaner installation. However, in the case, depending on who you're talking to, the jurisdiction of putting CalSil in there is not by the mechanical contractor, but by the insulator or the insulator contractor. In the same respect, depending on the system itself, CalSil would be put on a higher heating system versus a chill water system that might have urethane put in its place. Either way, that work, if done on a job, should be done by a trained, qualified person, and that person should be an insulator, in my humble opinion. So the correct practice of penetration, partition opening made large enough for the pipe to make its way through the pipe system, through the wall. No sleeve required. In some places, it is required through the spec, through how it's planned. Rigid pipe material such as iron partition, not moisture sensitive, such as CMUs. Penetrations need seal sleeves. When a pipe is flexible material such as PEX. Partition is moisture sensitive, such as drywall that Sean was talking about.
We did have a comment on where pipe goes through the exterior wall. The air barrier must be continuous to the pipe, not the insulation. When looking at the pipe insulation, you do need to have continuity of that air barrier. So the pipe jacketing should go all the way through that sleeve penetration and be continuous for the pipe. And then if it is an exterior wall, for air barrier continuity of the building itself, you also need to seal the building penetration to that exterior jacketing of the pipe with some kind of foam material, caulking, something like that, adhesive tape, some kind of material that's going to cover that building penetration and seal it to the pipe penetration so you don't have an air leak there. That would be a detail that you would have to add in for those types of penetrations as well.
So pipe and wall insulation practice, common practice. We see either use wall cavity insulation to insulate the piping as well, but pipe often placed inside of a cavity of the insulation, pipe itself uninsulated, potential issues. Heat loss to the inner wall or into the inner wall face, condensation potential for cold piping against drywall, which can be a health hazard. So that picture there actually showed that the piping was outside of the R13 insulation that they had, and it was uninsulated.
As far as the energy code requirements, this is the one exception where it's not just the pipe mechanical insulation section table that we're looking at for pipe insulation thickness. So usually we see this type of insulation for service hot water pipes. So one of the things impacted is the building wall cavity insulation. If you've got a pipe in there and it's compressing that wall cavity insulation, then you're not getting the effective U factor there. Again, we're also going back to R303 that requires following manufacturer's instructions for installation of insulation. Where if you have a pipe in that cavity and you're compressing the insulation and shoving it behind the pipe, you're doing a couple of things that are not code compliant. One, you're compressing that insulation so you don't get your effective R value. Two, you're leaving an air gap in that cavity around that pipe where you've shoved the insulation behind it. Now the other side of it has an uninsulated air cavity there. So you're not going to get as effective performance out of that insulation. So you're impacting the wall cavity insulation in a non-compliant way. And then also for the pipe insulation, for the commercial side, where most service hot water piping is going to have circulation systems on it, those are going to be required to be insulated. In the residential section, hot water piping, if it is circulated, so R403.4, R403 5.2, require insulation around the entire pipe to meet that it's R3 for service hot water piping in residential applications. But that's only for hot water pipe that has hot water circulation systems. If it's not circulated, then the pipe isn't required to be insulated because it doesn't continuously have hot water in it. But in most commercial applications, the pipe needs to have insulation all the way around the pipe. It needs to meet that table C403.12.3 value. Uninsulated pipe in the interior of the cavity insulation is not going to be compliant with that because only one side of the pipe is going to be insulated. The part of the pipe that's facing the drywall or has the insulation shoved behind it is not then insulated, so it's not compliant.
And I've seen that a lot, Sean, when it comes to jobs. They'll actually say we don't need to insulate the pipe in the wall because we're putting bad insulation in the wall that would satisfy the R factor or the R value of the what's needed to the pipe. And yeah, they do put bad insulation in the wall, but like you said, in many cases they'll only insulate one side of the pipe, and the other side is left exposed to whether it be drywall or just to the open air within that cavity. See it a lot.
Yeah, so best practices here is to insulate the pipe and the wall cavity independently, that you ensure the pipe has that R3 insulation around it. For the table C403.12.3, it's got that proper thickness and conductivity rating all the way around the pipe. And then you insulate the bad insulation, cut it, trim it however you need to fit around that pipe and insulation without being compressed, and then fit it in that wall cavity. That gives you full compliance and ensures that there aren't going to be any issues. If you're dead set on using cavity insulation to insulate your pipe, you have to find a way to bracket that pipe in the center of the cavity where you get that R3 insulation from the bat all the way around the pipe, including to the interior. Again, the little caveat here is this applies to hot water circulated systems or chilled water piping if it happens to be a mechanical system with chilled water piping in the walls. If you're looking at a residential application where you're not circulating that hot water, then this doesn't apply because that pipe isn't required to be insulated. It's only for hot water circulated piping systems and mechanical system piping, where you have to have this insulation all the way around the pipe.
So the next section we're going to talk about is some downspouts that you may see on jobs. So the picture on the right are the results of the condensation. And some people might say, well, it's a leak in the roof or other sources of where you're getting this condensation. In many cases, it might be the poorly insulated downspout, like the picture that you would see on the loft. So what they do, what I've seen in the past is using duct wrap insulation instead of a more instead of an elastomeric insulation for the downspout heads. So metric insulation is what we would call rubber insulation, the black insulation that's rubbery that you would put up that covers the head coming off of the downspout, and then using the insulation. Everything else seems to, even what we were talking about, the hanger distribution, doesn't seem proper. You can actually see crushing on the insulation. So whoever did this was either untrained or in a hurry, or was not being compliant, and that's the results that you'd see.
On the energy code side, for most roof drains, there isn't a specific code section on insulating those roof drains. It's covered by the roof insulation system itself. Has to have that minimum 1-inch insulation now with the 2021 IECC at roof drains, scuppers, and gutters. So that's kind of your condensation prevention, where around the roof drain isn't going to, the code used to allow you to go down to taper down to no insulation there. Now you have to have that minimum of 1 inch. But you still have a little bit of condensation risk around the drain pan itself. And that's where Bob's talking about some elastomeric insulation there can help prevent condensation. But because those downspout gutters are not conditioned fluids, there isn't an energy code requirement to insulate those. That's more in the building codes to prevent condensation and water damage, that those need to be insulated.
So the next picture that we have up here is a proper method for the most part, about 90% proper. We'll get into that in just a moment, but a proper insulation of interior downspouts. As you can see, you have the elastomeric insulation up at the top, at the base of the roof head there, and the insulation coming down. They actually dug out for the hanger, so there was an improper hanger put on. The insulator dug out for that hanger. Downspouts and heads surrounded from the above insulation, completely insulated. Standard industrial practice is to insulate the head with the elastomeric insulation, the rubber insulation. The insulation is a closed cell system, so thus airtight. However, once again, the hanger was buried, and as you can see, as we go down towards the to the vertical drop, they stopped at the first 90. Many specs will actually say on a commercial job that you'd have to do the horizontal all the way to the first 90, including the first 90 going down. That in this case, he may have been value engineered out, and the insulation for those 90s were removed and not done either by the owner, by the GC, or by the insulator themselves. But it should actually have the first 90 done going down. And then airtight butt joints. This is a suboptimal common practice. Dirt, improper application pressure, and other issues prevent proper seal between the butted insulation sections, resulting air gaps, moisture, air, and contact pipe would equal to a CUI potential. And you can see that there's actual compression and crushing from the longitudinal connections of each pipe covering, piece of pipe covering fit. You can also see that the longitudinal seal, the lap, you can see specifically on the left, furthest left piece of insulation, it's not smoothed down tightly, as well as the longitudinal 90s aren't sealed down properly as well. Overall, very sloppy job, very sloppy appearance.
For the energy code, again, we're going back to proper installation in C303.2. So where you have these joints butting together, the manufacturer's instructions detail how to keep those aligned, how to clean that surface in preparation for the taping material that gives you that air seal to make sure that stays in place. So you have to follow those instructions. And again, if you do leave a gap at those butt joints, now you've got a thermal break in that insulation where you've got a section of pipe that's not insulated. You can get, if that tape breaks at all, now you've got moisture penetration into that pipe, and now you've got a condensation under insulation potential. So making sure when you're installing these pipes, you can see a couple of sections in the image here on the right where there's not quite alignment with that insulation. So there's some offsets there. They try to just tape over it. And then you can actually tell there's a little bit of space between those because there's an indentation at both seams where that tape was put on tightly enough, it's compressed into that missing insulation air gap there. So now there's just air there, but no insulation. And so got to make sure that insulation is butted tight together before you tape it. And then when you do tape it, that it's properly aligned and that tape is sealed properly to hold those joints together.
And this is a picture of depicting a proper sealed method. Clean work, all gaps are sealed, all butt joints flush to the insulation. You could see that the street word for that is that the reducers in the insulation are painted tightly. It's not paint; it's an actual weather sealer that's put on there. The street word there he says is, did you paint your end cap or your ends? And it's not; it's actual sealer. But very nice job here that you would see.
We're a little short on time and we've gone a little bit over, so we're going to zip through these last couple of slides and then we'll answer some of the questions that have come into the Q&A chat there.
And so this is a real quick, the installing elastomeric pipe insulation. You should have some kind of mitering. You can't, when it comes to doing a 90, you will have a compression and a stretching of the throat and the heel. If you slide the insulation around, stress eventually will tear the insulation, and butt joints often not sealed with appropriate adhesive.
So for code implications, again, C303.2 requires installation per the manufacturer's instructions. Those instructions often detail mitering of the joints to get a proper seal. So looking at the images here on the right, for T-joints, you've got a bit of mitering there so that you've got a tight insulation wrap all the way around the pipe, even at that T-juncture. For corners, it advises putting little slits on the throat of the pipe so that when you compress it onto the 90, that interior insulation isn't compressed and stressed to the point where it's going to pop that seam apart for that insulation. So again, looking back to C403.12.3, you have a required insulation thickness and conductivity. If you're compressing that insulation or stretching it apart, that elastomeric insulation, when you stretch it, thins out, which reduces its R value. When you compress it, you're compressing out the air pockets and things in that insulation that give it its R value. So again, you're not getting the same performance. For elastomeric insulation on line sets outside the building, you have to have that weather protection on it. So there needs to be some kind of coating on the outside that gives it vapor protection, protection from UV light. Sometimes we see this as a paint on white coating. Sometimes it's a separate actual clamp on weather protective barrier on the outside, PVC or something like that. But there needs to be that protection. Looking at service hot water piping, if you're using this elastomeric insulation for hot water piping, again, you've got to meet those R value requirements. On the residential side, you have to meet that R3 instead of going back to the table R values. You have to have the R3 for the residential applications when you're circulating heated fluid in those pipes. And so you then would have to follow the manufacturer's instructions, which include the mitering to maintain that proper insulation thickness and prevent the stresses that can pop that insulation apart.
And this is an example of what Sean was talking about, miter 90s. It does have the UV protective coating. Once again, if you don't put this coating on, it's not a paint, it's a coating. Once again, so we get the idea that it's not a paint. So you just can't go to the store and get a paint to put on it. It's a specific UV protective coating that goes on, a weathering protection coating, and eventually, and that will stop drying out, the potential drying out and destruction of the insulation itself.
Something else to make note of, again, here, sometimes we see electrical tape or duct tape used to seal joints and hold this insulation together. Adhesive tapes are not allowed. Again, it can delaminate and then you don't have the tape there holding those joints together, providing protection. Or if you're doing maintenance and you have to pull that tape off, you can damage the insulation and require more cost to replace it. Zip ties are also discouraged. We've seen zip ties on these as well. Because you're such a thin point is holding that insulation together, it compresses there. And so the insulation eventually tears around those zip ties and fails. You're not getting the R value at the zip tie itself. I've actually seen condensation dripping off the zip ties that have been zipped onto this elastomeric insulation. So make sure when you're installing these that you have proper thickness, you're mitering those joints, you're using, when you're butting these joints together, you're using an elastomeric um, uh, rubber cement to seal those joints
Yes.
together. And then you're providing that protective coating on the outside as well.
And one more thing, Sean, is when you put the rubber glue on there, that it actually it's you don't put you put the you put the glue on both what you're the system that you're gluing the pipes insulation itself. If you're going to insulate from rubber to rubber, you have to insulate. You have to put the rubber insulation glue on both pieces of insulation, not just one, and then glue it on. It butts to the glue is adhesive to the other piece of glue adhesive. If that makes sense. A lot of word. There was a little bit of a word
Yeah.
salad there, brother. I apologize. And improper VAV box insulation connection. So at the terminus of a VAV box, the practice used to be where you just insulate the ductwork and you kind of leave you backstitch the end of it, you put it right up against the VAV box. But we've been going away from that practice that we'll show you in the what you need to do is you actually have to put some of the tape onto the VAV box to seal the system itself. So blanket insulation is not taped to the VAV box, as you can see in this picture, is not a good practice. Air movement between the insulation and the duct negates insulation placement. Sealing plenum often connected to outdoors, making condensation on ducts a concern. Heating from the reheat coils lost in the plenum without heating of the space as well. A lot of times you'll see when you butt up to they'll leave the coil itself uninsulated. Back in the field, what I used to do is I used to go right over the coil and then leave the uninsulated piping for maintenance open on the VAV box. But you should seal the ductwork to the VAV box as a practice.
For the energy code compliance, again, when insulation is required by the code in unconditioned spaces and on outdoor ducts, that's when this is now mandated by code. A lot of times this insulation is again in place for noise control purposes and not actual insulation needs if you're installing this on an interior plenum. We do note that as a best practice, even though it's not required by code, some insulation on supply ducts in these plenums is a good idea because a lot of times these plenums are under negative pressure. They're an open plenum for the return instead of a ducted return. And so it's under negative pressure and can draw in outside air. And we have seen where uninsulated ductwork will sweat and drip condensation onto the ceiling panels. So again, this is only a requirement when required by the code in an unconditioned or outdoor space. You're not going to have VAV boxes on the outside of the building. So really this only applies if it's in an unconditioned space where the energy code is going to mandate this kind of thing. But again, as Bob states, it's best practice to do this kind of insulation work, even for insulation inside conditioned areas.
And this is the picture of how it properly should be done, and that's taping it up to the the VAV box and actually covering the coil. As you can see, there's so many projects specify insulation over the VAV box coil. Extending insulation over the coil avoids losses to the plenum. The tape should be secured to the VAV box after coil is enclosed enclose the heat to the system. So this is what is a proper way that the insulation to a VAV box should be done. The conclusion, most of the projects performed in the state of Illinois are done per plans and specs. Sometimes issues arise that degrade the quality of installations. Um, Value engineering, rush schedules, confusion on responsibilities. Shortcomings can have significant impact on systems longevity and efficiency. Can also have impact on the health and safety of the facility.
So we've reached the end. If you have any follow-up questions that we haven't addressed, please feel free to reach out to me at energycodeillinois.edu, or feel free to use this QR code, reach out to Bob at the Heat and Frost Insulators. We'll touch on a couple of things that have come in to the chat and the Q&A. We had one question here. Can Bob please speak on the length of insulation metal shields, the saddles for hangers, I believe he's talking about. Sometimes he sees 4-inch long shields used, which can be too short for a hanger to stay on the center of the shield. 12-inch long shield is better. You have any comments on that?
Yeah, no, I've actually seen, that's a great question. I've seen where they've actually made them really short because of the situation where the placement of 90s are, where they'd have a 4-inch saddle as saddle hanger, and then you have 12-inch, which is usually a standard, and you'll actually see in some of the photos that we've given you, they actually have a center point where it actually puts the saddle or the hanger itself like almost like a rib within the saddle, and it equidistant center to the saddle. And then I've seen them 18 inches long. I've seen them in very thin grades where you can bend the metal with your hand, and I've seen them where they're very thick, where you needed two people to pull the saddle open. So best practice, the standard is 12 inches that you'd usually see that saddle on. Sometimes they have a little ripple in them, and then sometimes they're just completely smooth.
Another comment here: in cold climates, it's better to have a separate stud wall or chase for piping that is interior to the insulated exterior wall. That is true in most situations, but as energy codes are allowing, almost requiring more and more now, continuous insulation to the outside of the wall cavity, that can offset the need to build those interior stud wall chases, where if you load up on that exterior continuous insulation, number one, it reduces how much insulation you have to install to get the same performance factor, and it can open up those cavities where now it's easier to do maintenance and run plumbing, wiring, all that other stuff in those stud wall cavities. So yes, if you're going to go with an insulated stud cavity, it's better to build another interior cavity or chase to have your insulated plumbing and other utilities run through that interior stud wall. Or alternatively, you can start going more and more toward exterior continuous insulation and leave that stud wall open for those utilities without filling it with cavity insulation, or giving you a little bit of leeway in the performance of that cavity insulation. And then we had another question about should an outdoor application of the elastomeric insulation be coated to be finished with PVC jacketing, given the 2-year lifespan of that white UV protective coating? So the energy code is always material agnostic. It's mainly detailing performance requirements. Sometimes those performance requirements are going to be priced out, like when we're talking about stud wall cavities. You don't want to build a 20-inch stud wall to meet the R30 or R20 wall requirements in the current code. So if you want to stick with a typical 2x4 framing, you're going to be working with more continuous insulation on the outside. So in that regard, the code might push one type of application over another. But in this instance, looking at the insulation of the elastomeric insulation, it will allow you to use that paintable coating, with the understanding that in the owner's manual for the building, there is the manufacturer's information on that coating that says this needs to be reapplied every 2 years as a maintenance practice. And the building owner needs to be aware of that for those systems. But it is a good point that is a maintenance practice that often gets overlooked.
That's a great point.
And that appears to be all the questions we've had come in. Again, if you have other questions, please reach out to us at energycode@illinois.edu. If you have specific applications of insulation or projects questions, feel free to reach out, Bob, at the Heat and Frost Insulators using that QR code on the screen.
And
Thank
Sean,
you
if
all for joining us today. Sorry we ran a little bit long.
Sean, if there's any issues and they get a hold of you, they can always talk to us as well, right? You can
Yeah.
lead them to me as well. So for sure. Thanks.
Thank you all for joining us today. We hope it's been a helpful session for you. This will be uploaded to our website soon, so you'll have access to these slides and a recording of the presentation. If you weren't able to stay the whole time, you'll be able to catch any bits and pieces that you missed. So thank you all for joining us today. Hope you have a wonderful afternoon.
Thank you, everyone.